Okay, let's go ahead and look at an example of how to calculate and perform the analysis of a one-sample hypothesis test. We have an example here. A United Nations report shows that the mean family income for Mexican migrants to the United States is $27,000 per year. A farm labor organizing committee evaluation of 25 Mexican families reveals a mean to be $30,000 with a sample standard deviation of $10,000. Does this information disagree with the United Nations report? Apply the 1% significant level. Okay, so to analyze this problem, let's go ahead and open up the starting file. Okay, once we open up the starting file, we have the problem statement here, just in case you need to look back at some of the information provided. I would recommend going through this problem and documenting everything you know from start to finish. So let's go ahead and read the problem here again. The United Nations report shows that the mean family income for Mexican migrants to the United States is $27,000 per year. This is going to end up being the value that we are going to compare another value to. So we're going to compare sort of this standard 27 to see if this other report, who's reporting 30,000, is statistically different from this 27. So all of the information after this first sentence is related to the study that we're comparing against this first value in the statement. So I'm going to document this as value. This is what we're comparing against, 27,000. Let's go ahead and provide some formatting. Since we're talking about money, how about a green format? And let's go ahead and provide at least with the comma style there. Okay, so now a farm labor organizing committee evaluation of 25 Mexican families. So this is going to be the sample information that we're comparing a sample to this value. We want to prove or disprove that this sample that we've collected has enough statistical evidence to conclude that it is, in fact, does it actually disagree with this study. So anyway, let's go ahead and document the N value here. N value will be the 25 families. What else do we know about the problem? This study revealed that the mean for these families was 30,000. Let's go ahead and document that. And so we're going to call this the sample mean. Let's just call it, let's just call it sample mean with a sample standard deviation of 10,000. Okay, what else do we have? Does this information disagree? This disagree is our keyword. So I recommend documenting this keyword as disagree. And we also are given the level of significance for our test. So let's call this alpha at 0.01. And let's go ahead and apply some general formatting here and here. Okay, so this is everything we know about the problem, and the trick about actually investigating these is to essentially pick out the keyword and understand what this keyword is telling us. Now, disagree. So what does that mean? Well, we can disagree two different ways on this problem. I could statistically say 30 might be above 27. Statistically, I know it sounds weird, but we could say maybe it's less than the 27. So in this particular problem, we're actually testing both tails. So this implies, and sometimes I'll go ahead and write the implication here, implies a two-tailed test. Because if 30 was statistically greater than 27, that would disagree. as well as if it was under 27, it would also disagree. So we're testing both sides of the 27. Okay, so that is the key of this problem, that you can correctly identify this keyword and pick out the right test. Okay. Now at this point we're ready to go ahead and try to determine what test it is we're going to run. So let's go ahead and look at that formula sheet. Okay, let's bring up the formula sheet, and the first thing I want to do is just look at this section where it relates keywords to how you should write your null and alternative hypothesis. So disagree is a keyword that is similar to, is there a difference? Difference could be positive, could be negative, more than, less than. Is there a change? Well, a change could be greater than or less than. It could happen simultaneously. Or on the other hand, the one-tailed tests are just testing one direction. Is it greater than? Is it less than? Those are two different tests. We're in a situation where we're testing both. So we're actually testing this instance here. So I'm going to go ahead and copy this. We'll notice that the equal sign is in the null hypothesis. Always will be. You'll never, ever, ever write an alternative statement that has an equal sign. It is not equal, or it is strictly less than or greater than. Never an equal. So remember that. Let's go ahead and copy this image. And let's go ahead and apply that to the right spreadsheet here. And again, this is just to help you visualize the problem and understand a little bit more about what it is we're actually doing, because statistics are it requires some sort of visual element of, at least I think, to understand this completely. It's an abstract idea. So let's go back to our sheet, and I'm going to paste this figure, which is just a general figure, I might add. And now let's go ahead and write our null, H0. Our null hypothesis is that our sample mean, we'll call it mu, or let's say we actually call it sample mean above. Our sample mean is equal to the value. Our H1 is that our sample mean is not equal to. And this is the shorthand notation in Excel for not equal. You actually would use that in formulas if you were trying to program the not equal to symbol. Okay, so we have our rejection rules. So now it's either going to be a reject null if a z, absolute value of a z, was greater than a z with alpha divided by 2, or a t absolute if it is in fact greater than the t alpha divided by 2 at a degree of freedom n-1. Okay, so that's a little complicated to comprehend unless you have extensive experience. So what that is actually referring to is comparing the test critical with the test stat, the test statistic, in other words. And this figure down here shows a little demonstration of how to interpret these results once we have identified whether this is a situation for a z-test or a t. So we're going to reject the null if the test statistic lies in the rejection region. It can lie in the rejection region from the left or on the right hand side. So we are going to calculate the critical values, two of them, one positive, one negative. So that negative one would lie here. The positive would lie here. If we use an alpha value of 1%, instead of having 95 here, we would actually have 99% unshaded and just 1% shaded. The 1% here would be 1 divided by 2, so 0.5% on the left tail, 0.5% on the right tail. That summed up equals our 1. Okay, so again, this is a general figure and just meant to give you an idea of how to interpret these problems. So we have the two-tailed test or a non-directional test. It's actually the directions are both ways, right and left. Okay, so now we have to make up our minds what test we're going to conduct. Is it a right tail or left tail? I'm sorry. Is it a t test or a z test? So I'll write t or z, question mark. And let's see, T or Z. So if we were given specific information about the population, we could use a Z. Let's go ahead and go back to our problem. Right here, we can't assume that there's only 25 Mexican families in the world. So that is, of course, absurd. So this is information about a sample. So 25 Mexican families, we know there's a lot more than that. So this is a sample. If it's a sample and we're not explicitly told that for the entire Mexican family population, a certain standard deviation is occurring, we have to assume that this is a t, since we're not explicitly told that this standard deviation is coming from the population. It in fact says sample standard deviation. If that's the case, we have to use the t. So use t test because no information is given about the population. In other words, population standard deviation is not known. Okay, so I'm going to move around these figures just a little bit so I have enough room to display this text. And this is what is making us determine which T or Z to use, and we're going to use the T. So that means I'm going to calculate a test statistic and then actually two critical values. So let's call this T critical upper bound, if you will, and T critical lower bound. Let's call this LB and UB, upper bound and lower bound. Lower bound refers to the most negative on the left side, and upper refers to the most positive, the right hand side. Okay, so let's go ahead. I'm going to go ahead and apply some formatting here. And we need to know how to calculate these values. So let's go back to the formula sheet. We know this is a t-test, and we know it's testing both directions. So we're going to calculate t based on this. X minus mu divided by the standard error. Okay, so x minus mu, x bar is going to be the value from our survey. Survey says $30,000 minus our mu, or our value of 27 that we're comparing against, divided by standard error. Standard error is sample standard deviation, divided by square root n as in 25 Mexican families. Let's go ahead and enter that. We have a test stat of 1.5. Okay, I immediately look at this and say, okay, that's not so far away from the center. Again, remember that the center is 0. That's the standardized score of that. So we would have to have critical values that were even closer to 0 in order to reject the null. So what I'm trying to say is 1.5 is most likely in this do not reject because it's not out far enough to be close to the region of rejection. But that's just an assumption. We've got to actually calculate this. So how do you calculate the critical upper bound? Let's go back to our formula sheet and scroll down. We know it's not a z-test, so let's just ignore all of this. Go to the first line. Are we testing both directions? Absolutely. So we have critical lower bound, a critical upper bound. Let's go ahead and implement the lower bound first. The lower bound is here, second one I wrote down. We need to know alpha. Alpha is 1. And degree of freedom is going to be n minus 1. So we have a value here, it looks like negative 2.5 0.78. Let me take off some decimal places. Since we read left to right, let's go ahead and reverse this order. Reading left to right, reading top to bottom. This is a more logical format. The lower bound first, then we'll calculate the upper bound. So let's just switch those two. Let's go back to the spreadsheet and copy the formula. And you don't need to copy this. You can go ahead and implement that yourself if you'd like to. Let's paste that in here and supply the information of alpha and degrees of freedom, and we have the same value. That's a good sign. Okay, so when we are doing a two-tailed test, the upper bound is exactly equal to the absolute value of the lower bound. Okay, so that's good. And actually, if you look at the formula, the only difference here is that I'm multiplying the negative by the lower bound, the negative side, by -1. So T inverse two-tailed absolute value degree of freedom is what the Excel formula takes. Okay, so now the important thing is we've got to make a conclusion about this. And let me just go ahead and copy this one. Conclusion. Okay, so are we going to reject the null or fail to reject it? That's statistical lingo. So that's how most statisticians would report this. You're either going to fail to reject it, which means do not reject it, or you're going to reject it outright and accept the alternative. So let's take a look. I know my critical bounds are way out here at -2.8. Let's go ahead and draw this. So let's bring up Paint, and I'm going to draw this distribution. Looks something like this. And I'm going to connect that. We have a center, and we have a value range here of our minus T critical, and we don't even need to put in the numbers. We have a positive test critical, and then we have the T stat. So let's fill in the rejection regions. We have something that looks like this and this. These are supposed to be straight. The rejection region, we're going to reject the null if the test is in these regions. So let me just type that. This is the reject region, and same thing over here. Those are the reject regions. So the question is, where is our test stat? Our test stat is 1.5. It's positive, so it's roughly here, we'll say. We know it's at least greater than 0 and less than this test critical positive. So I'm just going to write TS, our test statistic. So we are actually not in a rejection region, so we're going to fail to reject the null hypothesis. Fail to reject the null hypothesis, which means essentially that the United Nations report is statistically equal to the Farm Labor Organization committee evaluation. So let's try to summarize that, which means the two reports are statistically equal. That's what that means.